Hey everyone, welcome back to The Explainer. Today, we're going on a really fun visual journey to demystify an absolute classic coding interview problem: balanced binary tree validation. You know, if you've ever found yourself just staring at a tree data structure, wondering how on earth to efficiently prove its structural integrity without writing an absolute mountain of convoluted code, well, you're in the exact right place. We're going to break this whole thing down step by step.
Okay, let's dive into this. What exactly makes a binary tree perfectly balanced, right? It sounds so simple on the surface, but as we're going to see in a minute, the logic required to actually validate it can honestly trip up even super experienced developers if they aren't careful. We really need to wrap our heads around this core puzzle of maintaining equilibrium across every single branch of the structure.
So here's the golden rule we need to live by. A height-balanced binary tree is simply one where no nodes left subtree and right subtree have a height difference greater than 1. That's it. But, and this is a massive but, here's the critical constraint you gotta remember. For a binary tree to be considered balanced overall, every single one of its subtrees must be perfectly balanced too. You literally can't just check the root and call it a day. That rule applies all the way down to the absolute deepest leaves of the tree.
And this brilliantly illustrates what happens when that golden rule gets broken. If we zero in on node 7 and look at its children, its left subtree has a height of 0. I mean, there's just nothing there. But its right subtree, stretching down through node 9 to node 6, has a height of 2. So the difference between 2 and 0 is, well, obviously greater than 1. And bam! That completely violates our core rule. This specific subtree is officially imbalanced.
Now, to actually catch this programmatically in our code, we need a bulletproof way to figure out the height of any given subtree. The core intuition here is really just that a tree's height is equal to the depth of its deepest subtree, plus 1 to account for the root node itself. This creates a really elegant natural recursive relationship. We recursively check the deepest subtrees, and then those calculated height values metaphorically just bubble up from the bottom leaves all the way to the top. Of course, as you probably know, every single recursive function needs a rock-solid base case, right? Otherwise, we'd just be stuck in an infinite loop forever. For our height calculation, the base case is incredibly straightforward. Whenever our traversal hits a null node, basically meaning we've stepped right off the bottom edge of a leaf, we simply return a base height of 0. That's it. It just gives our logic the solid foundation it needs to start building upwards.
Let's move to and see how this builds in practice. Watch how these recursive height calculations bubble up from the bottom. The null leaves return 0, which means the bottommost actual nodes return a height of 1. Now, as we trace this bubbling process up the right side of the tree, we hit node 7. Its left child returned to 0, its right child returned to 2. We do the quick math, find a height difference of 2, and boom, we've identified the imbalance right there on the spot.
But wait a second. Actually, hold on. There is a massive flaw in just calculating and returning these heights. Think about what happens right after we detect that imbalance at node 7. If all we do is return node 7's total height to its parent, which is node 5, well, node 5 has absolutely no idea anything went wrong down below. We've effectively tricked the parent node into thinking its branch is totally fine, and it might incorrectly validate the whole entire tree is perfectly balanced. Not good.
Now, what's really interesting about this slide is how we actually fix that fatal flaw. We desperately need a way to tell the parent that the subtree below it is totally compromised. Because remember, if even one subtree is imbalanced, the entire tree is ruined. So our elegant fix? We use a -1. Instead of returning the calculated height, the very second we detect an imbalance, we return a -1. This acts as a literal red distress signal. It immediately overrides any other math, bubbling all the way up to the root to save the entire tree from a nasty false positive.
Okay, let's look at how beautifully this visual logic translates directly into our Python implementation, step by step. First up, our base case. If the node is null, just return 0. Second, we recursively grab the heights of the left and right subtrees. Third, and this is the absolute crucial distress signal catch right here. If either of those subtree heights comes back as a -1, or if the absolute difference between them is greater than 1, we immediately return -1. Stop right there. Only if it successfully passes all those safety checks do we finally move to step 4 and return the actual verified height of the current subtree.
So the crucial point is just how incredibly efficient this solution is, which is exactly what you want to emphasize if you're explaining this in an interview setting. Our time complexity is O of n, where n is obviously the number of nodes. Why? Because our recursive function traverses every single node in the tree exactly once, no wasted effort. And the space complexity? That's also O of n. The space is completely dominated by the recursive call stack. In the absolute worst-case scenario, like say where the tree essentially looks like one single long spindly line, that call stack can grow as large as the tree's total height, which is n.
And there you have it, folks. By combining a really slick, bottom-up recursive height calculation with that clever -1 distress signal, we've built a robust and highly efficient validator. It's like a game changer for this problem. So I'll leave you with this thought. Armed with this new strategy, will your next binary tree pass the test? Seriously, try coding this out from scratch today just to really cement the pattern in your mind. Thanks so much for joining me on this explainer, and as always, keep building, keep learning. Catch you next time.